Welcome everybody. This presentation aims at illustrating the purpose and the use of OpenMAUVe, an open source Modelica-based simulator for underwater vehicles. Within this video, I will discuss the gap that led us to decide to develop another simulator, despite the many alternative tools already available. Next, I will illustrate what specific simulations are enabled by this framework, what features and performance you can expect, and finally, I will showcase how you can play with the software and reproduce the results. The work presented in this video was developed as a collaborative effort between three institutions: the University College London, the German Aerospace Center, and ERISA. The code developed for this simulator is released open source at the link provided in this slide, which is also reported in the description of the video. First of all, I want to acknowledge the use of AI-assisted technologies, which we employ to generate the logo of the simulator and the icons which you will see in this presentation, such as those reported in this slide. Specifically, we employed Deep AI, which is a free online tool to generate images from a textual input and which is linked in the description of the video. Now, this presentation is split into two main sections. In the first section, which is covered by a deck of slides, I will describe the simulator with its purpose, limitations, the reasons behind the need to develop a new tool from scratch, concluding with a design example and with the validation of the results. In the second part of the presentation, I'm going to cover the technical software aspects of OpenMAUVe, showcasing first how to load and run the models, next how to test the performance and independently validate the simulator, and finally how to modify the existing templates. In this section, I will focus on two vehicles specifically, namely the Rogue glider and the Sea-Wing glider, for the reasons that we will discuss in the dedicated section. First of all, OpenMAUVe is designed with the twofold purpose to be at the same time a simulation tool of underwater vehicles and a tool supporting the hardware and software design of such vehicles. Specifically, with this work, we are targeting complex autonomous underwater vehicles, and I will cover in a moment what I mean technically with complex underwater vehicles. Also, in this presentation, I will use the term autonomous underwater vehicles to generically refer to a plethora of underwater platforms, such as traditional AUVs, which are underwater vehicles using thrusters as main means of propulsion, and naturally ROVs, but also underwater gliders and hybrid vehicles. The key unique feature of OpenMAUVe is that this simulator aims at promptly, or in other terms simply, streamline the design of complex vehicles, test their dynamics, and finally evaluate their performance. If you already have a physical vehicle, you can simulate its dynamics with OpenMAUVe, or if you are designing a vehicle, you can test how the vehicle behaves with different physical components, such as with different actuators. On top of that, you can employ OpenMAUVe to test guidance and control algorithms with different combinations of sensors and actuators. As we will see later in this presentation, at times the same vehicle can be equipped with different sets of actuators and sensors, and they might lead to different dynamic performance, which once again you can promptly test within this software tool. For the same reason, the simulator can be used to investigate the behavior of a vehicle under faulty conditions, for instance by removing a thruster when a fouling event occurs. To successfully design and produce such a tool, there were a few technical features which were required, such as the capability of implementing multi-body dynamics, which is a key distinguishing element with other software tools already available, the possibility to simulate weeks-long missions within reasonable computational resources, namely requiring clusters or high-specs computers, and finally designing a fully open-source simulator which can be independently verified and customized. For this latter reason, we selected Modelica as programming language of choice and OpenModelica as the IDE of choice, so that everyone can freely access the code and develop further features. Now, I want to disclose from the very beginning the key limitations of this tool. First of all, OpenMAUVe is not a graphically advanced 3D simulator. This means that you will not see any fancy 3D renderings or jazzy underwater animations in this presentation, nor when playing later on with the simulator. Second, OpenMAUVe is not a computational fluid dynamics tool, Hence, when you are developing the dynamics of your vehicles, you need to estimate your hydrodynamic efficiency in other dedicated software programs, or anyway estimating them analytically from other sources. Finally, post-processing is natively a lacking feature in OpenModelica, and we necessarily inherit such a limitation within the simulator. Let us now proceed more specifically to the technical motivations behind the design of this new software tool. Assume that you want to develop a control system of an autonomous underwater vehicles. The typical design process encompasses a few well-known steps, which is anyway worth recalling briefly to illustrate the differences that OpenMAUVe introduces. First of all, you start by developing an analytical model for the physical system that you're targeting. You then come up with a system of ordinary differential equations, which are usually 6 or 12 ODEs for traditional AUVs and ROV modeled as single rigid bodies. Following, oftentimes, a simplified model for control purposes is devised, usually by linearizing the nonlinear dynamics. And at this stage, the full nonlinear system of ODEs is implemented in a dedicated environment, and the control system is tested in the simulator. The performance is verified, and if needed, a few iterations of the control system tuning are carried out until the performance is deemed satisfactory. This overarching modeling, simulation, and testing paradigm has been used for many decades, and a great deal of effort has gone into each one of these different stages, but overall, this process natively shows a few limitations and critical points. First of all, the model of AUVs, especially underwater gliders, are convoluted to develop and are extensively developed only for the case of vehicles with one internal mechanism, where here I'm referring specifically to underwater gliders with one shifting mass and one rolling mass. Analytical extensions are surely possible, but they result in large systems of ODEs associated to the many rigid bodies involved in these dynamics, requiring very specific technical skills and surely representing a barrier to advance the vehicles in this field. Second, the implementation of large systems of ODEs is rendered particularly complicated by the many nonlinearities arising from the dynamics of these vehicles, both from the hydrostatics and hydrodynamics perspective, rendering once again the testing of the performance of the vehicle more complicated and making the testing of onboard control system in a reliable simulator particularly challenging. Third, when we are talking about multi-body dynamics, which are the most appropriate modeling paradigm to describe underwater gliders and hybrid underwater vehicles, the dynamics are even more convoluted to simulate, as they might give rise to systems of algebraic differential equations which cannot be handled easily by standard solvers. This comes from the fact that the reaction forces exchanged between the internal moving actuators and the vehicle hull do give rise to algebraic constraints, which might translate into algebraic loops which requires handling by expert users. For all these reasons, we decided to develop a dedicated simulator environment which can tackle a large set of underwater vehicles, whether they are modeled as a single body or multi-body dynamics, as we believe that there is a clear gap in the possibility to promptly simulate complex vehicles, slowing down the development and testing of advanced platforms. The new pipeline, which is enabled by OpenMAUVe, is now showed in this slide, which allows to mitigate the problematic steps which we have just discussed. For instance, if needed, OpenMAUVe allows to skip the full analytical derivation of the ODEs, or in general of the full nonlinear model of these underwater systems, and allows to implement the system based on physical connections or physical assembly, rather than on the implementation of the explicit analytical model. This point will be made clearer soon with the example that I'm going to show in this presentation. Additionally, one can devise a simplified model for the guidance, navigation, and control of a vehicle and test the performance directly in OpenMAUVe. Similarly, if you have a vehicle and you want to test how it performs with a different sets of actuators, you can once again use it in such a new tool. Now, I keep talking about complex underwater vehicles, and I'm finally going to disclose what I mean with such a term. The vehicle illustrated in these pictures is called UX1, which was developed by the UNEXMIN consortium. In these specific pictures, taken back in 2018, you can see how this vehicle encompasses the standard actuators, namely the thrusters, but also an internal rolling mass to change the pitch of the vehicle. This vehicle can be, of course, modeled with a set of nonlinear ODEs, but as we said before, the model quickly gets really convoluted to implement in a standard causal analytical simulator. As you can see on the right-hand side, I modeled this vehicle with a system of 12 ODEs, covering the 6 linear and angular accelerations of the vehicle hull and the 6 linear and angular accelerations of the internal pitching mass. There is an exchange of reaction forces between the two bodies, and this type of occurrences give rise often to algebraic loops, which, as I mentioned earlier, are not always easily to break. Additionally, some vehicles can be equipped with different diving configurations specific to the mission they are carrying out. On the left-hand side, you can see a SeaExplorer glider developed by Alseamar, which is mounting for this specific mission a dissolved CO2 sensors developed by ProOceanus. As you can imagine, this underwater glider has a nominal control system, which has some intrinsic robustness to the dynamics parameters variation. But before deploying this glider for a real mission, you do want to verify whether the system is robust enough and can cope with the shift of the center of mass and the center of buoyancy by making sure that the vehicle can dive stably and the performance doesn't degrade too much. On the right-hand side, you can instead see an AutoSub long-range traditional AUV developed by the National Oceanography Center, which is mounting for this mission a turbulence microstructure sensor attached to the front of the vehicle. Once again, this configuration changes the geometrical properties of the location of the center of mass and the tensor of inertia of the vehicle, and to make sure that the vehicle can cope with such changes in the configuration, you do need to do some tests beforehand. Finally, as we discussed before, it is also important to be able to simulate long intercontinental missions spanning over several weeks or potentially even several months. To this aim, OpenMAUVe moves away from the classical flat Earth navigation assumption, relying instead on the inertial reference frame based in the center of the Earth as the Earth-centered inertia, which you can see in red here. We also use the ECEF and NED frames as additional coordinate frames, which you can see rotating in. I will now move on to a design example, which I will cover in a few slides to provide an overall idea on how to use the tool, and then I will repeat the same exercise in the actual simulation tool. On the left-hand side here, you can see a blended wing hybrid glider, which is, as of April 2025, being developed at University College London. I will add a reference in the description of the video for those of you who are interested once the work is published later on. As you can see, the vehicle encompasses several internal actuators, such as one rolling and one pitching mechanism, two variable ballast devices, and, even if it's not depicted in this figure, a thruster positioned at the aft of the vehicle and a few control surfaces. During the design of the vehicles, we weren't exactly sure how many actuators and hence how much redundancy we wanted to embed on board, and we are currently exploring different configurations thanks to OpenMAUVe. Let us assume that you have developed your own vehicle, such as this UCL glider, and that you want to implement and test the performance in a simulated environment. You can finally see how OpenMAUVe actually looks like in this software interface on the right-hand side. As you can see, there are several blocks which we are going to cover one by one as we gradually expand the complexity of this tool. The first element in the model of the blended wing glider is the wet hull, highlighted in the red dashed circle. The hull model implements the dynamics of a rigid body, so including the nonlinear effects such as Coriolis and centripetal effects, and the added mass. The model can be instantiated just by dragging and dropping a dedicated icon and connected to the other elements of the vehicle by means of specific connections. The actual code is embedded in a dedicated interface, which we will further see later on. Next, in the specific case of the blended glider, we have a set of movable masses, as I was mentioning, which encompass one actuated shifting mass and one rolling mass. When opening this model, you can notice a few nonlinear blocks, such as the saturations covering the mechanical limits and the proper dynamics of the actuators associated to the use, for instance, of electrical models or motors. In this hybrid glider, there are also two variable ballast devices which are used to generate additional buoyancy forces. The buoyancy force is again saturated to the physical limit associated to the volume of the actuator and implements the dynamics of such an actuator. The other blocks represent the physical connections to the different frames. Once again, this model implements a set of differential equations, of which we are seeing here only the graphical representation. Later on, I will also illustrate the presence of virtual sensors used in this specific case of the variable ballast device model to measure the position of the vehicle with respect to the inertial frame, which is needed in turn to implement the direction of the buoyancy force generated by the actuators. As I mentioned earlier, when you want to test different diving configurations of the vehicle, you can quickly implement such change by dragging and dropping an additional rigid body and check whether it is mostly convenient to position the new actuator with respect to the associated body. In this case, I added a point mass located at the very front of the vehicle, which is defined by in this case, by its own mass and inertia tensor, which can be moved around, simulating the physical connection to the hull. The clear advantage in this case is that you don't need to calculate the overall inertia tensor of the vehicle in different configurations, but the simulator internally computes the tensors based on how the different rigid bodies are connected automatically. Now, after having briefly showcased the flavor of the simulator, I would like to spend a few words on the validation of the results produced from this tool. As you have noticed, OpenMAUVe follows a different modeling paradigm, which is not the implementation of the analytical expressions of the whole dynamic system, but rather the implementation of the analytical expressions embedded in a single model, and then the assembly together of this model. Now, as this is a change with respect to the standard protocol, we need to make sure that the validation process is solid, to make sure that the results produced are in fact trustworthy. For this reason, we are not just interested in comparing the results of OpenMAUVe with other simulations of underwater vehicles, which of course are many and well established, but we are instead specifically targeting complex vehicles. In other words, we are less interested in comparing the results with other AUV or ROV simulator, but we are rather interested in simulating complex vehicles such as underwater gliders or hybrid underwater gliders, which have these internal moving components. Naturally, the list of such complex vehicles shrinks pretty quickly. We especially found a substantial difficulty in finding publications and open source datasets which cover the full list of geometrical parameters, including the value of all the masses, their relative positions with respect to the center of the body fixed frame, the full list of the hydrodynamic coefficients, the data of a full deployment encompassing also the control input for all the actuators, and finally the ground truth data or the measure data for that deployment. This led us to shortlist for the validation stage 2 underwater gliders, which are the ones illustrated here. On the left hand side you can see the Rogue experimental underwater glider, which is a small version underwater glider for pool testing. On the right hand side we have the Sea Wing underwater glider, which is on the other hand a full-fledged vehicle which was developed which was deployed in several missions for data collection purposes. You can find the references to both these works in the associated publication, and I will further discuss the results of the validation in the software section of this presentation, which comes next, when I will showcase how to run the simulations, reproduce the results, and independently check the results produced by the tool. Now, I'm just going to wrap up this part of the demo using the slides by summarizing pros and cons of the presented simulator. Once again, the key feature of OpenMAUVe is the implementation of a modular design, allowing to promptly develop complex vehicles. This means that you can assemble and simulate complex vehicles within a few hours of work rather than a few weeks or months worth of work. You can promptly implement different actuator sets for the reason we saw before. The simulator has been compared with other public data, which we will discuss in a moment. The simulator is open source, so it's fully customizable. There are ways to interface this with external software tools via functional mockup unit. There are also low computational resources required, so we will run this demo on a standard office laptop without GPUs or any high specs. And finally, as OpenModelica is an open platform, is a multi-platform tool, naturally OpenMAUVe is deployable over different operating systems. On the other hand, the OpenMAUVe is not a visually advanced 3D simulator, as I mentioned earlier on. The post-processing features are still lacking, and due to the fact that OpenModelica by design is still not an advanced post-processing tool. And finally, there are a few technical limitations in the implementation of the dynamics, such as the lack of the implementation of currents models and surface effects. There are no reasons why this cannot be done in the future. We just, at this stage, don't have it, and just want to disclose this as well. Now, I will move on to the software demo, the proper software demo, in a second, within a new interface.